So we're going to talk about what deuterium is and how it plays such a central role in our health, and what is the relationship with some disease processes and how to control deuterium levels in our body. And there is a link here in the bottom where you can find original data and also discussions about deuteronomics. Now, to know what deuterium is, we have to start with hydrogen. And hydrogen is the lightest chemical element. It's when it's forming gas, it's a transparent, odorless, colorless, and tasteless gas. So it's very inert with our body, and it's a multi-purpose fuel by oxidation. That means this is what we use, hydrogen, to power our cells and power our body. And this process happens in the mitochondria. So here's hydrogen. It's the periodic table. You probably remember this from school. The red arrow to the left, upper left corner shows hydrogen with the mass of 1 Dalton, which is the atomic mass unit, and the rest is pretty much derivatives of the proton that hydrogen carries. It's right here. You can see the proton with the blue mark or the blue ball at the center of the upper left picture, and there's a little electron circling around it. This is what hydrogen is. And if there's no electron, we just call hydrogen the proton. And the name of hydrogen comes from hydros, which is water in Greek, and it's practically shows that actually hydrogen is in water, meaning that we consider hydrogen as water when it attaches to oxygen. So when you talk to a physicist and they ask how much hydrogen there's in the room, they also kind of add the water pool that they can find in the room, meaning that hydrogen is really most closely related to water. And deuterium, just the pair or the stable isotope of hydrogen, is labeled as 2H, showing that it actually has a different nuclear structure. We're going to look at it in a minute. It's still transparent, odorless, colorless, and tasteless, but I added a short note that with a twice as heavy and large nucleus, we'll look at it. So it's very tricky to find just by sense, because it behaves very much the same as hydrogen, but it actually has a twice heavy, twice large nucleus, and it's not very friendly with mitochondria, meaning that mitochondrial oxidation is hampered by deuterium exposures, and we're going to talk about this in more details. So to the left, you can see hydrogen with the proton and the electron around it. And to the right, you can see deuterium with a proton, a neutron, and an electron. And as you can see, the mass is vastly different. It's 1 Dalton versus 2 Dalton, so it's 100% increase in weight and nuclear size. And if you have a SUV vehicle compared to a passenger car, you can tell how harder it is to park in a tight garage, which is very much similar to like how we use these little cellular compartments to fit hydrogens and protons. So this is a mitochondria, and I'm just going to show you these little mitochondrial proteins, which are complexes, and I'm sure you heard about these. And to the right, you can see here the ATP synthase nanomotor, which is powered by hydrogens or protons. And as you can see, ATP is synthesized by transferring these protons into the matrix from the intermembrane space of the mitochondria. So this is practically a rotating nanomotor. This is how we call it. The protons arriving from the intermembrane space through a short tube, they attach to the side of this nanomotor, and on the other side, when they kind of spin around powering this nanomotor, they roll into the matrix, and in the matrix you can see ATP synthesized, and this proton will be attached to oxygen, and this oxygen with two protons will form water, and this is what we call matrix water or metabolic water or interfacial water or structural water in the mitochondrial matrix. Here Esther sped up the nanomotor a little bit so you can see how fast they actually run pretty fast, about 100,000. That's the fastest they measured in physiology per minute of these nanomotors. And here comes deuterium, which is twice as large and twice as heavy. And what deuterium does to these nanomotors, they break them. That means there's no ATP synthesis, there is no metabolite or food processing. Practically, it's a molecular crowding is what it causes. Deuterium high in food, because these protons, these hydrogens, come through food. And since these nanomotors are non-functioning, mitochondrial damage will lead to a number of diseases that we'll cover in a bit. So practically, we have to be careful of what kind of water we use in our cells, in our mitochondria, and what kind of water we produce in our mitochondria, and it's mostly dependent of the food we eat. So based on the hydrogen structure and the stable isotopes of hydrogen, if an oxygen is occupied by two hydrogens, water is produced, or we talk about water, which is to the left. In the middle, you can see semi-heavy water, which is one hydrogen, one deuterium, the heavy guy, and oxygen. And heavy water is actually two deuteriums are replacing two hydrogen and oxygen. It's trace. It's not very common in nature, but semi-heavy water we do have in nature. About 6,600 protons are supplied with one deuteron. So when we talk about fast and rapidly moving nanomotors, they may encounter a deuterium very easily. So we have to limit, we have to control, we have to regulate deuterium in our cells.